So, good afternoon, everyone, and welcome to this new LATI technical webinar. Let me introduce myself. My name is Luca Posca. I am the Technical Service and Marketing Director of LATI. I take care of business development in general, and today I am very pleased to share with you all a short introduction about what is the situation, what is the ongoing situation concerning the relationship between self-lubricating thermoplastic compounds and incoming restrictions on fluorinated substances, which are normally used as self-lubricant additives. This webinar is intended as a scientific piece of information. There is no marketing inside, and I would like to put the stress on a very important topic, on a very important point. Even if this is a scientific webinar, I will not use an academic approach. I wanted to make the topic as easy and as comprehensible for everyone. So I will make some slight imprecisions, but I hope the most skilled and the most technical people among you all will not be mad at me. So while we wait the last attendees to join the meeting, let's just give a look at our agenda, which is quite crowded, I would say. First of all, we will have to make a short resume, a short introduction to what is wear and friction in polymers. Of course, no more than a couple of slides, just to recall what are the key factors playing a major role in wear and friction when it comes to plastics. Then we will try to understand why PTFE is such a fabulous additive, is such a wonderful substance, and where do all the properties of PTFE come from. Then we'll try to understand what is the situation. What is the situation concerning perfluorinated alkylic substances and fluorinated polymers and incoming restrictions that are going to be enforced within 2 or 3 years. Then, of course, we will try to understand if there are alternatives to PTFE, what is LATI doing, what are the main driving forces, what are the main fields that we are exploring in seeking for an alternative to PTFE in our thermoplastic compounds, and then we will come to conclusions. We will try to understand what is feasible, what is not feasible, and let me say, what are the most reliable all-around solutions for the incoming future of thermoplastic self-lubricant compounds. So let's just jump into the topic. I will accept any kind of question at the end of this webinar. You can just dial your questions. I will be happy to reply if we still have the time. So what is wear and friction? Let's just introduce wear and friction as a scientific phenomenon. Let's consider two planes sliding one against the other. You have to put them in contact, you have to put them in relative motion. So one has got to slide onto the other. Let's suppose that we apply a force that is actually pushing one onto the other. We can experience and define friction as a non-conservative force opposing motion and dissipating energy as heat. We can experience this in our all-day life. When we wrap up hands, when we can just feel the heat on our hands sliding one onto the other. That is friction. Friction is actually dissipating energy as heat, and it is a non-conservative force. What does non-conservative mean? It means that its work is not related to the starting point and the end point, but also to the way the force works, to the amount of movement that this force is actually doing. Wear is a dissipation of mass, not a destruction, of course, is a dissipation of mass, meaning that you actually remove some mass because of the foretold phenomenon. If you have any interest in going more into details about friction and wear, I strongly encourage you to give a look at our previous webinar we made last year in 2022. I personally took care of that, and we tried to give a better introduction to friction and wear in thermoplastic compounds. But today this is not the topic, so it will just be a very short introduction. Let's try to better understand what is friction and why and how we can actually solve any friction related problem. If we zoom into the surface of the two sliding parts, the orange one and the gray one you see here, you will see that any kind of surface, even the flattest one you can imagine, actually shows some roughness. This roughness is the source of the issue. If we imagine to put into motion the gray part onto the orange one, and we imagine to apply some vertical force indicated with Fn, which could be the load or the pressure, we will experience a resistance to motion. That is the Fr indicated there. The ratio between the resistance to motion and the vertical force is defined as the friction factor, which is indicated by the Greek letter μ. Friction factor is a number, pure number, whose value is below 1, of course. Normally it's something between 0.4, 0.5, 0.6. With some plastic, it can go down to 0.1. If we give a closer look to the resistance to motion, we will find out that the resistance to motion is achieved by the mean of two major contributions. The first one is due to molecular interaction, and the second one is due to the plastic deformation of all those peaks and crevices you see on the rough surfaces. The molecular contribution is due to actually to molecular interaction, meaning that the two materials will tend to stick together because of electrostatic forces, because of van der Waals forces, and any kind of electrical interaction between the molecula. This will arise the so-called adhesive contribution, meaning that the two parts will tend to stick together. The other contribution is related to material deformation. So the peaks and the crevices just come in contact one onto the other. You have to spend some work, some energy to deform the peaks, and this will create some kind of resistance to motion. This is the mechanical contribution, and it is also extremely important in both wear and friction phenomena. So once we have understood where is friction coming from, friction is coming from mechanical contribution and adhesive contribution. But how is friction factor generated? Friction factor is due to a lot of different factors and parameters. Friction factor is depending on the normal force, so pressure, is depending on the roughness of the surface, the relative speed, temperature of the environment, thermal conductivity, and so on. These parameters here are common to all materials. So this relationship is worthy and is working for all materials. It could be ceramics, metals, plastic, whatever. But for polymers, we have also another set of very important parameters which are actually making the difference when it comes to friction. Which are these parameters? Glass transition temperature, defining the temperature where the amorphous part of the polymer becomes in a rubbery state. Then we have the crystallinity index, then we have the viscoelastic and elastoplastic behavior, we have time, and so on. This other set of parameters is absolutely applying to polymers. So you can easily imagine how hard and difficult and how unreliable actually can be all the tests that we make to measure friction. You see how many different parameters we have to take under control in order to provide some kind of reliable description of friction. One question can be anyhow easily answered. What is the perfect material? How could we conceive a perfect material? How should it work? For sure, we have understood that the perfect material must have a very, very, very low adhesive behavior. So it must show a very poor chemical, let me say, chemical activity. And it should be a material that we can easily deform. we can easily shear. This could be the perfect material. Let's move to wear. Wear is more or less originated by the same phenomena. We give a look at our surfaces, we apply motion as usual. We will see that in some areas, those peaks and some crevices and some crests, we get in touch. We'll weld one onto the other and will break as the motion is actually forcing the gray part to slide onto the orange one. We can evaluate the wear rate as a proportion including friction factor, and wear rate becomes lower as the material gets harder and elongation at break and stress at break become higher. So we can say that a perfect material should have a very low friction factor, should be hard, and should require a lot of work, which is actually related to elongation at break and stress at break, should require a lot of work to be broken. So we can also introduce in this case an adhesive component of wear, which is actually related to the tendency of the molecule of the gray part and the orange part to stick together one onto the other. When they weld one onto the other, they are forced to break as soon as you have motion. Then you have the abrasive component of wear, which is actually due to the so-called third body, meaning a very hard body which is actually rolling between the two. Then we have the fatigue wear, which is actually promoted by the poor capability of the material to resist applied cycles, applied stresses for a cyclic application. And then we have corrosive wear, which is promoted by the environment. But also in this case, we can ask ourselves, how should be done the perfect material? The perfect material, as I told you before, should show a very low friction factor, should be hard, and should require a lot of work to be actually broken, to be deformed and then broken. Now, what are the solutions that today we can find on the market? We have the classic solutions. Classic solutions are metals and ceramics. And you know, we can improve the behavior of metal and ceramics, adding some lubrication or adding some specific coatings, very hard coatings like silicon carbide or aluminum nitride and so on. As LATI, we work on the other side. We work on the side of plastics. So we select very intrinsically self-lubricating plastics like PEEK, acetal, polyamide, PBT, or polyethylene, and we introduce some extra fillers which actually improve and boost the tribological performance of those plastics like graphite, molybdenum disulfide, silicon, carbon and aramid fiber, and PTFE. PTFE is actually the best performing additive that we can imagine, and now we are going to find out why. Let's meet this guy, let's meet PTFE, and let's try to understand why PTFE is so well performing. PTFE is a very interesting molecule coming from the polymerization of tetrafluoroethylene. Tetrafluoroethylene can react with a very highly isothermic reaction, meaning that the polymer that will be born after this polymerization reaction will be extremely stable. The molecule in itself, here it is, PTFE, polytetrafluoroethylene, is a very, very, very interesting molecule. It is a very big one, very big, very heavy. Just to give you an idea, the molecular weight of PTFE is 1,000 higher than the molecular weight of nylon 6,6, meaning that you have a very huge, very bulky, very long molecule. You have a very high crystallinity index. PTFE is born with 95%, which is then reduced down to 40–50% during the subsequent processes. But in any case, it is a very highly crystalline polymer because of its nature. It's very linear and homogeneous molecule. And it's very high density. So it's very heavy, It's very big and it's very crystalline. But this is not enough to understand why PTFE is such an excellent performer. We have to look a bit closer to the bonds of the PTFE molecule. Let's jump into the PTFE molecule. If we give a closer look to PTFE, we will find out that the carbon-carbon bond, the covalent bond between carbon and carbon along the backbone of the PTFE molecule, the gray spheres you see there, this bond is extremely stable. It requires more than 350 kilojoule per mole just to be broken. But it is nothing when compared to the carbon-fluorine bond. The carbon-fluorine bond is among the most stable covalent bonds that you can find in nature. Its energy is higher than 400 kilojoule mole, and this is an extremely short and stable chemical bond. It also is extremely polar because fluorine just needs one electron to be perfectly stable, and it takes this electron from the carbon atom, and you have a strongly polar dipole, as we say. What does this mean? This means that you have a very short bond with a very high energy to break it, and this will lead the molecule to be absolutely stable. This means that even if you try, it is extremely difficult to break it. So you have the carbon backbone completely shielded and protected by fluorine atoms, and you have, because of this chemical inertia related to the strong bonds, you have very weak forces that keep the PTFE molecule one on close to the other. It is something completely different, just to give you an example, completely different from polyamide. Polyamide molecules are kept together by the strong hydrogen bonds, which have a very high energy. Why does this happen? Because polyamide is not, as we say, a chemically inert polymer. It has a very electrostatic active hydrogen and oxygen atoms. On the contrary of PTFE. PTFE is a completely inert, completely chemically inert because of the carbon and fluorine atoms, of the completely shielded by fluorine backbone, and so you have these long chains which stay together only by the means of very, very weak van der Waals forces. Now, we have understood that in the chemistry of PTFE is the reason of its outstanding performance. What does it mean? When you have such a stable molecule, you will have an extreme chemical inertia. What does chemical inertia mean? It means that there is no way to break it. There is no way to stick onto it, to glue it, to paint it. There is no way to overmold it, nothing. Nothing can actually stick to PTFE. There's a very low surface energy, so it's very hard to wet it. It's very hard to apply any glue or to apply any other chemical substance. And it has a very high thermal stability. Thermal stability because the chain of the PTFE polymer is extremely stable in itself because it does not want to break. This means that the product will have a very low friction factor because we almost have no adhesive force, and you have a very, very low amount of work to shear it. So it's a very soft, very, let me say, it's a very weak as a solid. It's a very weak solid. It is extremely resistant to the adhesive component of wear. It is not resistant to the abrasive component of wear. But all in all, what we can say is that thanks to its overall properties, it can work very well with any other polymeric matrix. So you can actually disperse PTFE in any polymer from polypropylene to PEEK, and you will always have outstanding performance. Now, let's try to understand how it works in the compound. First of all, I have to focus your attention on a collateral effect of PTFE. In case you want to think about replacing PTFE-based thermoplastic compounds with a non-PTFE-based thermoplastic compounds. PTFE has a huge effect on shrinkage. Remember this is absolutely important. PTFE increases both transversal and longitudinal shrinkage. The more PTFE you put in your compound, the higher will be the difference between unfilled and PTFE-filled compound when it comes to shrinkage. So I would say forget about replacing one-to-one PTFE-based polymers with PTFE-free based solutions, because you will have I would say, bad surprises when it comes to shrinkage. But this is just a technological issue. What is really important to us is to understand how PTFE actually works in our compounds, to understand how we can replace it. Today, LATI produces a wide range of PTFE-based thermoplastic compounds. We use any kind of thermoplastic-based polymer, from polyethylene to PEEK, and we use PTFE with a huge amount of different additives. We use it unfilled, we use it with silicone oil, glass fibers, carbon fibers, graphite, aramid fibers, and ceramics. So if you check out our website, you will find hundreds of so-called LATI-lube compounds containing PTFE as a main self-lubricating additive, because it works absolutely fine. And today you can rely on plastics that can actually be used from 80 to 300 degrees C, featuring PTFE as a main self-lubricating additive. How does it work? How does PTFE work in compounds? For sure, many of you will already know this, but it's important to understand it very well. Now, let's imagine we have a PTFE-filled part, the gray one. The white bubbles are PTFE. You have the orange part sliding onto the other. At the beginning, you have some burn-in phase. The first step is the removal of surface roughness. You just remove all the crevices and peaks and valleys you have on the surface. Then you start shearing PTFE chains. Remember that PTFE chains are kept together only by very weak van der Waals forces because of the very high chemical inertia. So you can actually shear the crystals of PTFE and shear the molecule, and you can actually laminate it on the surface. You can shear it and move it into the valleys, and you can actually level the surface just by rubbing PTFE onto the surface because of shear. If we zoom into one of those white bubbles, you will see that because of the mechanical stresses, you can actually promote chain breakages. So you can actually break the chains of the PTFE chains. What happens when you break the chain of a polymer? You create radicals. You create radicals which are extremely active chemical species, which are prone to react very quickly, and these chemical species will react with the orange part. This means that the PTFE radicals will stick onto the orange surface, promoting the so-called film transfer. So you will have PTFE not only on the surface of the gray part, but also on the surface of the orange part. So you will have PTFE on PTFE with extremely oriented chains. You will have a solution that works great for high loads and low speed, and you will have a solution that works fine from 5% to 20% of PTFE in the thermoplastic matrix. That's exactly how PTFE works. So very poor adhesion and film transfer. These are the keywords. Now let's come to the bad news. What happens when you heat up PTFE? I told you that the molecule is extremely stable. That's exactly the problem. PTFE has a glass transition temperature of 126 degrees C. It's stable up to 260. It should melt at 327, but actually it doesn't melt because of viscosity. But from 350 on, it starts thermal decomposition, and that's the problem. You have a full depolymerization above 650. And what happens when PTFE decomposes? When PTFE is broken because of temperature, it will release a lot of very nasty substances. First of all, fluorhydric acid, which is extremely corrosive and extremely dangerous for people's health. Then it will release a huge amount of very nasty oligomers, so-called oligomers, meaning small molecular, fully fluorinated oligomers. Here are some of them. And of course, it can release also fluorinated free radicals, which are nasty and extremely reactive as well. This is the problem. This is the problem. These substances are the bad news. What are the so-called PFAS then? The PFAS are just what we have been talking about, are the so-called poly or perfluorinated alkylic substances. It's just the amount of guys that we have just met in the slide before. I will introduce you the first PFAS, the perfluorooctanoic acid. Perfluorooctanoic acid is a fully fluorinated organic acid, so it is a poly or perfluorinated, meaning high fluorine content, alkylic substance, meaning that the main chain is coming from an aliphatic hydrocarbon, and substance, meaning that it will define as well as substance, even if it is alone or in combination with other substances. What are the main problems related to these byproducts of PTFE degradation? They are extremely persistent, meaning that it is almost impossible to destroy them because of their inherent extremely high stability. They lead to bioaccumulation. They are very mobile. You can find them everywhere all over the world. You can actually find it in the North Pole. They are extremely toxic and ecotoxic, and they are the so-called ubiquitous presence, meaning that they are everywhere. So you have nasty substances, very toxic, extremely stable, very mobile, that can be found everywhere. And that's the reason why today we are asked for PFAS-free solutions. Very nice question, very difficult answer. Now let's give a look at what is the status, the state of the art of the rules. Fluorinated polymers have been identified as a PFAS in 2013. You can see this is one of the branches of the diagram describing what is PFAS, but you can easily see that fluoropolymers are identified as PFAS. So PTFE, PVDF, PFA, and so on, ECTF, and so on. All these fluorinated polymers are PFAS. So what is going to happen to octanoic acid is more or less happening also to PTFE. It was PFA was introduced in the substances of very high concern list in 2013, 2014. Then it was a new regulation in 19. In 2020, there was the first limit of perfluorooctanoic acid content in PTFE, just to give you an idea, 25 parts per billion. And today we have 5 European states pushing for a further restriction covering a wide range of PFAS, including fluoropolymers. What is the roadmap? The roadmap is very tight. March 2023, we had the first 6 months of consultations, have just ended in September. Now in 2024, there will be an assessment of all social economical issues related with the ban of fluorinated polymers. But between 2026 and 2027, it is very, very keen the introduction of restrictions on fluorine polymers. Of course, there is a lobbying. We are trying to understand, to make people understand that fluorinated polymers are extremely important for many strategic applications for Europe and UN climatic objectives. So we're actually lobbying to try to convince these guys, these people, that fluorinated polymers are very hard to be replaced, but the hope for a general derogation on fluoropolymers is really very low. There is really a little chance for success. So by 2027, we are almost sure that PTFE will be forced to be removed from our plastics. And this is a big issue, Now let's make our ideas clearer. Let's imagine that we have to replace PTFE today. First of all, we have to understand what is needed for plastics to create a successful self-lubricant polymer. We need extreme chemical inertia. First of all, we need a plastic, an additive which is not prone to react with anything. Then we need thermal stability. We need a good processability. We need good viscoelastic and mechanical properties, of course. And then we need an acceptable price versus performance ratio. This is of course, I put it as the last problem, but you know, for many situations, it's the first issue. Let's see what are the closest solutions. I will start with the very first one. I would say the most popular one, the easiest one. It's already being transferred also by LATI and many of our competitors since a few years. It is the ultra-high molecular weight polyethylene. Ultra-high molecular weight polyethylene is a very big chain, polyethylene chain. It is a polyethylene, even if it has a very funny name, but is a big chain of polyethylene with a very high molecular weight, very high crystallinity. The density is lower than PTFE, of course, but it also shows an outstanding chemical inertia. So we have most of the properties of PTFE. I also put another important topic on the table. It has a much lower melting temperature, and this could be an issue. But if we look at the global warming potential, just to give you another hint, the global warming potential of ultra-high molecular weight polyethylene versus the same value of PTFE, we can find that ultra-high molecular weight polyethylene is not only a very good additive for self-lubricating polymers, but it is also a very interesting solution to reduce the carbon footprint of self-lubricating plastics. Do not trust this number that much, but I am absolutely sure that at least polyethylene has a much lower global warming potential than PTFE. What is LATI doing? LATI has already been compounding ultra-high molecular weight polyethylene since a few years, I would say. We have solutions based on nylon 6, copolymer 6 and C6, polyolefins, polycarbonate, polyethyl sulfone, and PPS. So first bad news. We have a much lower number of resins where LATI has tested as working ultra-high molecular weight polyethylene. I repeat, it's a LATI experience, it's not global experience. Also from a filler point of view, we have been working with ultra-high molecular weight polyethylene in silicon, glass fibers, carbon fibers, and aramid fibers. Now we are working also with other synergies, but as you can see, the combination is much lower than the combinations available for PTFE. Also, the available maximum temperature of these lubricants, self-lubricants plastics, is lower. Why? Because we found out that it's very difficult to properly disperse ultra-high molecular weight in high temperature plastics. So in PEEK or PPA or stuff like that, or polyphenol sulfone and so on. It's very difficult to have a proper dispersion of this additive, and this leads to, let me say, to very poor performances as a self-lubricating additive. Let's give a look at the numbers then. I tried to compare very similar formula here. I do not want you to lose your mind in trying to understand this. I just picked up the same base resin, the same amount of reinforcement, and the same amount of additive filler. Please remember that these percentages are weight percentage, and remember that PTFE has a density which is twice the density of polyethylene. So from a volume point of view, you have 1/2 of the volume of PTFE compared to ultra-high molecular weight polyethylene. What you see here is that from a friction point of view, polyethylene works fine, but as far as LATI experience is concerned, we were not able to assess a satisfactory friction wear performance. So friction is okay, wear is not okay. Why wear is not okay? We are strongly convinced that the main issue is dispersion of the filler. So it is a technological issue. It's not a, I would say, it's not a chemical issue. But let's move forward. To sum up what is ultra-high molecular weight polyethylene, we can say that the molecule in itself has a very low friction factor, is very resilient and wear resistant. So it has a very low density versus PTFE, and it has a very nice amount of other good properties. It's colorable, does not plate out, it's not corrosive, does not contain halogens, and it is PFAS free. So a lot of very interesting properties. On the contrary, the disadvantages: dispersion can be really challenging, it is not suitable for all base polymers, and the wear performance up to date has not been as satisfactory as PTFE, but maybe this issue is due to dispersion of the additive or the testing method. Now, let's try to understand what other solutions could be viable. I would say that the most promising ones we are already working on are polymer-to-polymer replacement. So we would like to replace PTFE with other polymers, which show more or less the same behavior. PEEK, polyimides, thermoplastic or thermoset, polybenzimidazole. These molecules share with PTFE an excellent chemical inertia, excellent thermal resistance, are intrinsically self-lubricant, sorry, are suitable for viscoelastic and mechanical properties. Too bad they are extremely expensive and their performance and processability is still to be tested. But in my humble opinion, this is the most promising future of PTFE replacement. Then we have the so-called exfoliating fillers. LATI is already using it. It's molybdenum disulfide, graphite, and hexagonal boron nitride. Why do these fillers work? Because they are made up with weakly bonded layers, which can actually slide one onto the other. Being so mobile, you can actually experiment the self-lubricity of these fillers. Because of the sulfur, they can somehow transfer onto the mating part, and you can also have a very nice filling of the surface. So you, using this kind of exfoliating fillers, you can actually even the surface of the of the mating of the two sliding planes. When it comes to compare the performance, I wanted to compare 1% molybdenum disulfide with PTFE, and also in this case you have more or less the same friction factor, but the wear factor cannot be actually compared. The wear behavior is much worse. So PTFE is also outperforming molybdenum disulfide in this very case. Then we have fibers. There is a lot of development on the fiber side. Classical fibers, carbon, glass, and ceramic fibers. They work very well by preventing the effects of adhesive wear. They just keep aside, they keep away the two surfaces, the two mating surfaces. They are very hard, they increase the surface hardness. They work like this. So they put themselves between the two surfaces. They work fine up to 15–20% content. Above that content, they can create issues because they can easily detach and promote third body wear, and this can be a problem. Then we have aramid fibers. Aramid fibers are a special kind of polyamides. They have very high strength, high wear resistance. They work very well as a standalone. We are already using it as LATI. That's exactly why they work so fine. They're very promising, but I think today aramid fibers must be studied from a synergy point of view, and we will see later what does this mean. And then we have an interesting new thermoset group of fibers, polyimide fibers, which can actually be dispersed in the matrix, working more or less as aramid. Very interesting because of thanks to their very high thermal and chemical resistance. This is the third field of development of for PTFE replacement. Then we have a huge family of ceramics, nanoceramics, nanofibers, nanotubes, and so on. First of all, we have this very hard nitride and oxide and carbide molecula are available. These molecula are also available in nanoscale. They work very well by promoting surface polishing. So they somehow create a very clean and flat surface by micro polishing. They can somehow promote film transfer. They are extremely hard, so they can somehow prevent from wear. The problem here is that these fillers can be very aggressive to your equipment, to the extrusion machine, to the molding machine, to injection molding tools. Then we have a new family of sulfides, not only molybdenum disulfide, but also copper sulfide, tungsten sulfide, zinc sulfide. Very interesting, very promising, all sharing this layered structure. They can transfer onto the metallic surface. We are working quite a lot on these alternative sulfides because some of them are very interesting and show a very interesting synergy with other fillers. Then we have the nano stuff, nano mica, nano clay, nano titanium dioxide, nano zinc oxide, and so on. Nano fillers work very well because of their dimension. They are very small and they can actually work down to the molecular segment, but they are very sensitive to filler and they can impact quite a lot the mechanical properties of the compound. So to summarize the behavior of these fillers, very interesting, but I would say the most interesting part of these fillers is the synergies that can actually be studied to improve the behavior of a primer, I would say a primer friction factor reducing additive. You have to mix this primary additive with some of these fillers and see what happens. The contrary is high cost, affecting mechanical performance, and then you have huge issues when it comes to handling, processing, and end-of-life safety issues. Because these nano-engineered particles, there is no restriction till now, but for sure we'll have a hard time as soon as we get more in details about what happens at end of life. When they are disposed, what happens when you release these nano-engineered ceramics into the environment. And then we have to explore the synergies. Synergy, I would say, is the keyword of this webinar, because you cannot replace one-to-one PTFE, but you can somehow get close to its performance by exploring the synergies between polymers, new polymers, and polymer modifiers, which are already available on the market, additives, as the ones I've shown you before, and reinforcements. Some of these synergies are already known. Just to give you an idea, PTFE and silicon, PTFE and aramid, molybdenum disulfide and glass fibers, graphite and carbon fibers, and so on. These are known synergies. You can already find plenty of self-lubricant plastics featuring this kind of synergistic combination. But then we have a huge amount of new synergies which have to be explored and which are actually being explored right now at LATIs or by our competitors, of course. Some of them, carbon fibers and boron nitride, secondary polymer and boron nitride, glass fibers and alumina, some of those metal compounds and ceramics, and so on. Very interesting, huge potential in these synergies. That's exactly where we have to work. Which may be the next steps then? For sure, we know that by 2027, PTFE will have a hard time. But what can we do between today and 2027? I would say that we can start trying to reduce the PTFE content. Just to give you an idea, let's say, put an example, below 5%. These will make no exception when the PTFE restrictions kick in. Even 1% or 0. something percent will be PTFE. So it will not be possible to use it anymore. But in the meanwhile, we can try to understand how we can reduce the amount of PTFE and still have a working product. So we have to work on the synergies between PTFE and other additives. Just to give you an idea, PTFE and the secondary polymer, PTFE and ceramics. And we are already working on this field, and we already have some very interesting products. Then I would say we have to evaluate the life expectancy of PTFE-free parts. It's not compounder job, it's the end user job. But what happens when you remove PTFE from your compound? It may happen that the life expectancy of your part is reduced by 50%, 60%, 80%. Is it worth? Does it make sense to have a PTFE working part which can last only 1/10 or I don't know what of a PTFE filled part? I wouldn't say so. We have to evaluate the sustainability of PTFE-free solution, keeping in mind that today you can find recycled PTFE, which is available and reduces quite a lot the global warming potential. And then we have to evaluate very, very carefully the alternatives to PTFE, because they can hide very serious processability issues, and I would say even more serious safety and health issues, especially when it comes to thermosets or some kind of funny nano-engineered ceramics, which can actually be nasty stuff. So let's draw our conclusions. What does PFAS-free mean for the moment being? It's a big issue because PTFE shows an outstanding set of properties. And when I say outstanding, I mean outstanding. PTFE cannot be replaced one-to-one with anything right now. Derogation for PTFE, I wouldn't say so. It seems quite unlikely. So between 2026 and 2027, PTFE is very likely to be put under the scope. I would say it will have a possible restriction. As a first step, we may try to understand if it is possible to lower the PTFE content, and in the meanwhile, we'll make a nice and healthy exercise trying to understand how PTFE work and how we can actually replace it. Ultra high molecular weight works fine, but not on any kind of thermoplastic metrics and not for every kind of application. Works fine for some friction issues, but for where, as far as LATI is concerned, we have not been able to find exciting results. Many alternative solutions are on the table, very interesting synergies to be explored. Many are soon to be released on the market, exciting numbers, but remember PTFE is still very far to be I would say to be emulated or to be caught. Last but not least, I would say that in the meanwhile, it will be also a very healthy exercise to revise the requirements of the applications, because if we imagine to remove PTFE, some applications will have big issues. So maybe it would be the right time to start re-engineering some parts, trying to consider if those wear requirements and those friction requirements are actually that necessary, or maybe we can somehow re-engineer our product. I really hope I was able to give you an acceptable introduction to what is the status of PFAS, PTFE, and the possible solutions that could pop up on the market in the next couple of years. I would say, just to finish my webinar, I would say that LATI and LATI's competitors are working hard on this. Now and then you see some news popping up, this guy has an outstanding product, these other guys have an outstanding product, but for the moment being, there is no, I would say, no groundbreaking solution. We are working hard to trying to understand mostly which are the synergies that can actually replace polyethylene, PTFE, but for the moment being, there is no exciting news, I would say. Now, if any, I would really be pleased to answer any question, if there is any question.
Okay, the first question, what alternatives are actually under development in LATI? As I told you, the most, I would say, the most interesting alternatives are polymer-to-polymer replacement, so replacing PTFE with some other polymer. These are the most promising ones. Then we are also working on some ceramics, which are actually providing a very, very interesting result. And I would say some of these grades are already available, have already been engineered. Some of them were a bit disappointing, but maybe it's a problem of ours. We have to understand how to properly process them the right way. A question about polyketone. Yes, polyketone is a very nice plastic, very interesting plastic. LATI had already developed a full range of polyketone-based self-lubricants, but then we had some bad surprises related to the chemistry of polyketone, and we found out that it was not so easy to process it. So we prefer to hold all those solutions for a while, as long as polyketone producers are not supplying a better version of the resin. It's already available on the market, and we will start working on polyketone again pretty soon. Okay, a third question concerning the test used to measure friction and wear. As you know, there are tons of tests that are actually available on the market. If you read the literature, you will find plenty of different tests. Thrust washer, pin on disc, ball on disc, sliding plane, and so on. There are a lot of custom-made tests. After a long, I would say, a long and excruciating experience, LATI has decided to create its own LATI method. Today, you can find on our website, on our database, friction and wear factor are determined by using the LATI method. The details are available in case anyone is interested. It's very complicated to get a solution providing the most reliable number. As you can see, as you've seen, friction and wear depend from thousands of different parameters, not thousands, but from many parameters. It's very hard to hold some of them, constrain some of them, and work on the other ones. In any case, today I think I would say we have engineered a very reliable testing method, which is close to ball on disc. We are setting the temperature, we are setting the load, the angular velocity, and so on. So the numbers you see on our website are quite reliable. But remember, they are just as reliable only for comparison. They are not describing a physical property of the plastic. Another question, which solution could be better for electronic components that shall support reflow processes? Very good and very interesting question. Reflow means high temperature. So you need a high performance resin as PPS or a polyamide 4,6 or some PPA like polyamide 9T. On polyamide 9T, we have been able to use ultra high molecular weight polyethylene. On PPS as well, with interesting results. So I think that ultra high molecular weight polyethylene could be a possible solution, but please remember that we are borderline. Temperature of those plastics is very high. Ultra high molecular weight polyethylene has shown as very difficult to disperse above 300 degrees C. So I would say the PPS is already close to borderline. But to answer your question, I would say polyamide 9T or PPS with ultra high molecular weight polyethylene, or why not polyamide 4,6. LATI is not compounding polyamide 4,6. DSM is doing this job, but I would say polyamide 4,6 with ultra high molecular weight polyethylene could be a very interesting solution. Okay, now our time is over. If you have any question, please send your questions to my email address. You can see it here. I thank you all for your attention. I also thank the competitors who have been attending this webinar. I'm always happy and proud to see competitors attending our webinars. I think it is very important to share also among competitors ideas. I will welcome all your questions, and please keep an eye on our LinkedIn page and our YouTube channel. You will receive a link to this to the registration of this webinar in case you want to share with your colleagues. And I thank you again, and see you for the next webinar.